Good afternoon, my name is Roger Pierce and I represent the purple team. The rest of the people in my group are Randy McCauley, Stephen Snyder, and Ross, a bunch of consonants. This is the last presentation for the filter wash station with a concentration on proportional integrated control oil. See this week, goodbye offsets below reset point button. An overview, go through some background, steady-state operating curve, step response, the FOPDE model, sign response, relay feedback, root locus, the proportional controller, and the PI controller. Here's our system schematic. You want to tell me when I start?
Just press it down.
Just hold it down.
I know you're putting
No, you said about 10. I didn't know. 8, 9, 10. Right. One more? Okay. This is a graph of our Ks that we determined from our different methods for estimating for our system. Step up, the step down, the step up model, the step down model, and the SSOC slope, and also the Bode and the relay. As you can see, this mirrors our SSOC, where the K is very similar, but it does go down as you go up the SSOC. Here is T sub 0 for our system. We all agree fairly well with the value for this. And this is Cal for our system. Once again, we all agree fairly well on this, except for the Bode on the very high range. This is the root locus for the. These are the values that we were able to get. This is just for one region. Since ours are fairly similar, this is I believe Randy's. The critical damping for the root locus was 0.5. The 1/500 decay was 5.1. The 1/10 decay was 13, and quarter decay was 17, and ultimate was 25. And that's for a T sub I, the time constant for the controller of 2.2. Here is a tau sub I of 0.6 seconds. Very similar looking root locus. And here are the values from that. Critical damping is a value of 1, 1/500 decay, 4.4, 1/10 decay, 8.4, quarter decay, 11, and ultimate 17. Here is tau sub I of 9 seconds. So this is the third tau sub I that we had for our system.
See ya.
Now I can do it. Critical damping was 0.34, 1/500 decay, 4.8, 1/10 decay, 13, quarter decay, 18, and ultimate was 27. All right. So we had to actually verify that these values were correct. So for each region, we came up with this grid using the tau sub I to one significant figure, and K sub C with a max of 2 for anything. We put it into our system, and we were able to get the response and settling time and the K ratio if it was oscillatory. This is the 10 through the 12 pound mass per minute range. And the reset windup experiment happened at a KC of 5 and a tau sub I of 2 for this range. Here's mine, the 12 to 14 pound mass per minute output range. If it has a black bar on it, that means that for our experiment it never reached the set point. We have a max of 120 seconds. So if it never reached its set point in 60 seconds, it would never reach its set point in 120. So I just walked down and threw it out. We had a good response. It says monotonic. Good response at case of C at 4.4 and 1000.6, and it settled within 5 seconds. And we'll get a little later. That was what I thought to be the recommended settings for this controller.
Which one?
The 4.4 and 0.6, because it settled in 5 seconds. Here's the 14 to 16. Same kind of data. With low case sub C's, it took a long time for it to settle, such as like the 60 seconds settling time for case of C of 1 and tau sub I of 2. For tau sub I of 9 and a case of C of 0.83, it never reached a set point, so I blocked that out. And reset wind up occurred at 9.4 and tau sub I of 9. And here's an interesting thing about our reset windup. This is a graph from Ross, but it takes a lot for us to get a good reset and windup response. So for the values, they're actually still oscillating and when the set point changes. That's the only way we can get it, is if it's initially an oscillatory response. Because of the length of time that we could put in as a max for our system, we had to put a KC high enough and a tau sub I low enough for it to do this. And that was the reset window response. And I had errors, I didn't realize. So there and there. Okay. So recommending a tau sub I in a case of C. Our criteria, it should have a low settling time. It should reach the new set point fairly quickly, and it should be monotonic. So going back through, I picked the 4.4 and 0.6 case of C and tau sub I. And here is a graph of what you would get if you use that. And you see it as it goes quickly to the set point, the new set point. And boom, done.